So, good morning everybody. We have started week 5 already. Some portion I taught regarding heater treater and gun barrel. Heater treater and gun barrel. Okay, heater treater, actually you are giving heat. In gun barrel normally you do not add heat, but if required you can add heat. So normally gun barrel will be used for warmer environment where your heating requirement will be lower, but in heater treater actually you are adding heat, so you can use anywhere, okay, irrespective of your location. Now gun barrel normally it will be for multiple well where a large volume of fluid will be there, but heater treater like single wellbore it can be replaced. Gun barrel may not be used. You can use heater treater. So there are differences, but these days people are using some heating element also in gun barrel. So external heating possible, internal heating also possible. Okay, so now when we are saying heating, so there will be two things. One will be direct heating, and another will be indirect heating. Direct heating. Okay, when you are going for direct heating, like say inside your separator system you are giving heat, and the hot gas or hot fluid will be hitting the metal surface of this pipe. Okay, when it is heating up, directly oil or water mixture will be heated up. So this is called direct heating. But indirect heating, what you are doing, you have one separate fire source, and where you are heating water and increasing temperature and maybe hot water or steam you are producing, that steam will be circulated inside the your separator system, gun barrel or heater treater. So that means high temperature, whatever you are getting in heating oil, heating water, so that will be limited. Okay, so because limited temperature is there, so safety aspect will be very good. But if you are going for direct heating, so in that case temperature can go very high, so in that case accident prone, it is possible some accident also. So in that case you have to fit like water level sensor, you have to put your temperature sensor, you have to put some fire supply cut system, so that system can be made safe. Okay, so one burner system will be there, burner, or we can say combustion chamber, actually combustion. Okay, where combustion happening, when you are combusting something, actually you need two things. One will be air plus fuel. Okay, and another thing also required, heat. Air and fuel mixture in the atmosphere, it is not burning, but if you give heat, which will be starting initial reaction, like a small amount of fuel will be burning, it will create very high amount of heat. So that heat will be further hitting another fuel particle, and finally accident can happen. Or if it is useful for your application, for example you are cooking for your household application or IC engine combustion or your heater treater application, if you are controlling that heat and using for proper purpose, so in that case what you do, you put certain amount of air, certain amount of fuel, and give certain amount of fire spark. You may have heard this spark ignition engine. So you can create small spark, or a combustion ignition engine. So here you can create very high compression ratio, so the temperature can go up to the burning point or flammable point. Then air fuel mixture will burn, it will produce lots of heat. And I told you this is an exothermic reaction. Okay, so this is exothermic reaction, not endothermic. Exothermic reaction. Okay, CTION. Okay, so and air, how much air you have to give? You cannot give air whatever you like. Okay, you have to give air in controlled way. The term is called stoichiometric ratio. Okay, the stoichiometric ratio means, let's say air, 1 liter of air needs only 1 meter cube. Is 1 liter oil maybe requiring 1 meter cube air. Okay, now you are giving 1 meter cube air, means certain amount of oxygen is there, 21%. So that oxygen is exactly will be burning the fuel. So if let's say certain fuel plus oxygen you are reacting, and H2O plus some other component will be created. Okay, now you get very high amount of oxygen, means very high amount of air. Okay, very high amount of air we are giving, that when after burning the flue gas or burnt gas or smoke, whatever you are getting, going out of the system, so it will take lots of heat. So lots of air you are giving means the air also will take some heat and it will go out. So actual efficiency of the system will be lower, okay, because air is taking certain amount of, you are giving very high amount of air. Now some smart student can ask, sir, then we will be putting lower amount of air, then what will happen? If you put lower amount of air, what will happen? Fuel will not burn completely, okay. So fuel is not burning completely, so what will happen? Instead of CO2 in after burning a hydrocarbon, it will be producing CO2 after combustion, right? Hydrocarbon means petrol, diesel or any other kerosene if you burn, or coal, wood, it will be producing carbon dioxide, water and some other molecules. If you give low amount of oxygen, so instead of CO2 it will be producing CO, okay, carbon monoxide. Carbon monoxide is harmful, okay. Any engine designer or combustion chamber designer, their main aim will be to produce carbon dioxide, not carbon monoxide, okay. Carbon monoxide is harmful, carbon dioxide is not harmful. Although this greenhouse and all these things, they will say carbon dioxide, carbon dioxide, but in combustion engineers, aircraft engine designers, IC engine designers, your boiler systems designer here, they will try to produce carbon dioxide, not carbon monoxide. Carbon dioxide is not harmful, okay, because it is already there in the atmosphere, in body also producing carbon dioxide, but carbon monoxide will be creating problem, okay. So you have to give proper amount of oxygen, maybe little bit higher amount, okay, but lesser amount dangerous, okay. So your combustion chamber in heater treater system, it will have fuel system, fuel injection system, it will have air injection system. So control way you have to give air and fuel ratio, that ratio is called stoichiometric ratio, okay. So just exactly same amount of air whatever required for burning fuel, you are giving a little bit more, not less, okay. So this term you should remember, stoichiometry ratio, okay. Then you need one fuel source, one oxygen supply source, then fuel and oxygen controlling mechanism. For example, direct heating system, I said like temperature can shoot up suddenly, but water level can go up, go down. When water level is going down, then your fire box, that fire combustion happening that area, then that area temperature will be very high. So that system can melt and burning also possible, right? Leakage possible, rupturing possible. So in that case, you have to control the temperature. How to control? Cut fuel supply, not oxygen supply. Cut fuel supply first, then fuel giving less amount. So total amount of heat, exothermic reaction, total amount of heat you are getting, right? You see this my equation. So some delta also will come, delta heat, okay. So less amount fuel, less heat, so temperature will be going down. If further it is not controllable, completely cut this oxygen and fuel both, then you see, you check where is the problem, okay. Water level is going down, or maybe any other problem in the whole piping systems, or any leakage is there, or unnecessary fuel is going very high rate, oxygen supply is lower. So all these things you have to check, okay. So you will have one burner or combustion chamber. The combustion chamber may have like lots of pipes, normally in boiler lots of pipes will be there, okay. So combustion is happening, water is going through the flame, it will be like this. Let us say I am creating one flame source, okay, and water pipes will be like this, okay. So when water pipes are moving inside the flame, actually you can give one pass also, like say you have one combustion chamber, you are giving one pipe and flames are here like this, okay. But people will be giving multiple pipes. You know the reason? Reason is that you are increasing surface area, okay. Surface area increasing means, if you remember the convective heat transfer coefficient formula, HA delta T, right? Heat transfer equals HA delta T. Later we will discuss details about convective heat transfer, but the basic formula is HA delta T. H means convective heat transfer coefficient, okay. A means area of the pipe, surface area means how much contact area is there, okay, and delta T temperature difference. Now if you have one pass pipe, means total surface area of the pipe is low, but if I have multiple pass, then L into that pi d, right? Pi d means perimeter into L, so that is total surface area. So multiple pass means total area increased. So total my heat transfer rate increased. So heat transfer increase means whatever heat is getting produced, so everything will come to your water inside pipe, right. So that water you are passing through your boilers then. Okay, this is indirect type of heating. But direct type of heating, you do not need this sort of water pipe. Directly you are heating and metal surface. Let's say this is one box. Inside fire is there, so the box outside temperature will be high and touch anything touching like water, oil, anything, it will get heated up. Simple, right? The flue gas can heat directly things. Right? So when you are burning something, burning must be controlled way. So fire flames should not go outside, because in separatist systems in surface production operation, everything is safe. But if there is any leakage and if you have any fire source, that can be dangerous. So every fire must be within certain box or certain control system. Your air must be controlled, your fuel supply must be controlled, your temperature must be controlled, your pressure in the separatist system must be controlled. Okay, it should not go beyond certain limit, and you have to monitor also regularly whether valves are working, any valve is leaking, a temperature sensor working properly, pressure sensor working properly. Okay, okay. Now let's see how to calculate the heat transfer. Okay, we have seen some calculation in previous lecture, I think week 1 or 2. We will see some more calculation of heat transfer. Yeah, so we discussed gun barrel, right. So in gun barrel, normally I said like there will be no heating element, but we can give heat also. So how we can give? We can create one external heater. Okay, the heater will be supplying hot fluid inside gun barrel. Then you can create layer, you can get gas out, water leg you can create, like we had done already calculation, or directly you can take, and oil. Okay, so why are you creating water leg? Because using water leg actually you can control the interface level, okay, from outside instead of working inside the system. Okay, heater will have multiple coils. Okay, so hot fluid will be coming, it will be heated up, then hot fluid entering into your separate system. So this is heater, then fluid entering here. So some spreader will be there, so you are spreading the hot fluid, okay, inside water zone, not in oil zone. Okay, your spreader will be in water zone, okay, below interface level. Okay, so there you are heating, actually heating, or you are giving hot fluid. Okay, then slowly this what oil particle will be moving up and moving up, because of you changed already viscosity and density. Because of that oil particle moving up, you take oil, and if any dissolved gas is there, anyway, because of creating low pressure and high temperature, gas will be going out through this top section. Fine. So this is indirect type heater, and direct type heater, like one possible, like you have firebox inside and you can burn, okay, burn fuel and you can get heated. So we will calculate heat input requirement. So how much heat is required to increase temperature of within the heater. Okay, so theoretical heat transfer rate, you know, WC del T. W instead of W you can put M also, mass flow rate, QTH BTU per hour. Okay, based on this formula actually we will be solving some problem. So maybe you can note down this formula. M or W is called mass flow rate of liquid, alright, and unit is LB per hour, pound per hour, okay, and C specific heat, okay, at an average temperature. This is average formula. So specific heat at average temperature, what happens is a pipe is going inside and going back, okay. So when entering hot pipe, so inlet temperature will be higher, when pipe is exiting, so that temperature will be lower, okay. Then what will be the value for C? So in this case they are using C for average temperature, okay. It will not be average, but assume average temperature. Later we will modify the value for C and T, okay. Specific heat at an average temperature, okay. I am writing short AV only, so you can write full form average temperature, okay, and value will be 0.5 for oil and 1 for water. Okay, and unit is okay. So C value, the unit will be BTU per LB per degree Fahrenheit. Assume water mass 350 MASS pound per barrel. Okay, so unit conversion is given here. So if heat loss is 10%, so for 10% heat loss, because when you are transferring heat from one or transferring energy from one form to another form or transferring heat, there will be certain losses because heat is transferring, so radiation loss will be there, convection loss will be there, there will be some leakage somewhere maybe. So they are assuming less 10% loss will be there, like thumb rule. Okay, it may be more or less. Okay, so whenever any conversion is happening by second law of thermodynamics, you can remember first law says like the heat can be transferred from heat can be converted into work. First law says, but how much it will be transferred, it does not say. But second law says heat cannot be transferred 100%. Okay, you are converting heat to work, 100% conversion not possible. Some losses must be there. So that's why the irreversibility term will be coming. This is irreversibility. Irreversibility. Okay, this is some heat you converted into work, and again same work you are converting to heat. So you cannot get same amount heat again because lost again lost. So some energy will be lost. Okay, so that's irreversibly. So you change back to the system, original system. So some energy lost. That's why it is irreversible. But it's completely energy you are getting back, then it is reversible. Okay. So second law says, or Clausius statement, I think. Second law says heat or work, if you are converting or one form of energy converting another form, there will be certain amount of energy lost. Okay, so heat transferred from one point to another point, it will be flowing through pipe or some mechanism will be there. So there will be certain losses. So you cannot prevent that loss. Okay, there will be heat already it is there. There will be loss due to radiation, convection. Okay, if any other mechanical element like friction, rotating machine, other machine is there, so there will be heat generation losses. But here you are generating heat, so the heat generation loss is not there. Final form of any energy is heat. Okay, so whenever any machine element is working, moving element or IC engine or any other engine, so final form of loss, that loss part will be heat actually. Okay, but when heat energy is there, so loss is there in the form of radiation, convection, conduction also possible, like you are heating something and the material and all everything will get heated up slowly. So that is also loss, right? Heated up means MST, this formula you see, mass into C heat capacity, a specific heat, and del T temperature difference. So something is getting heated up means it is taking already certain amount of heat. So that heat you are not using, so that is lost. Okay, we are calculating only the usable heat, right? So we are assuming 10% heat is lost for this purpose. Although the designer will be trying their best to reduce the loss, but there will be certain loopholes where losses will be there. Okay, so there is no perpetual motion machine in the world. Perpetual motion means one machine you design, it will be running continuously, not possible. Okay. So Q equals Q theoretical divided by 90, 0.9. Okay, because 10% lost. Okay, so total heat input will be Q theoretical 16.2 del T. This formula Q oil flow rate, Sg of oil 0.5 plus Q water flow rate is G of water. Okay, then 1, water is 1 already I told. Okay, and why Sg is coming, if you see flow rate into density is equal mass. Okay, rho into Q equals mass actually. Okay, here we are using W, so we can say W. Okay, rho into Q. So flow rate, if you know, you multiply with density, it will be creating mass. And here we are assuming density constant because it is liquid. If it is gas, then density also will be changing. Liquid also compressible actually if you increase very high amount of pressure, but presently for normal application we are assuming density not changing. Okay. Uh, okay. Alternative way to calculate heat. Okay. So Q equals VO, as per book I am writing actually this VO, the symbol they are using instead of H or other symbol, VO A T M. Okay. Or A equals Q VO T M. Okay. V means field coefficient or heat transfer coefficient. So VO you can write heat transfer coefficient, heat transfer or film coefficient sometimes they say. Okay. Heat transfer coefficient varies if you change fluid, if you change surface profile, if you change fluid velocity. Let us say 1 cup of coffee I am taking, right, and in this room it will be cooling quickly because environment is lower temperature. Okay. Now if I have a fan also, so it will increase heat transfer rate. Okay. So it will be changing your H actually. What happens when certain fluid nearby my coffee, air, let us say air, and this is coffee. Okay. So coffee is heated, so coffee temperature is higher, let us say 60 degree, air temperature let us say 25 degree. Okay. So coffee will transfer heat to air, right. So nearby coffee surface, cup surface, what air particle will be heated up. Okay. Now if there is no airflow, so the air particle because of buoyancy to be moving up slowly. Okay. So because of buoyancy particle will be moving up slowly, and again fresh air, low temperature air will be coming on the surface, it will get heated up, again it will be moving up. So buoyancy means like again particle settlement formula, whatever you have calculated you can assume, right. So smaller particles slowly it will be moving up because of viscosity and density difference, right. Now if you have blow of air on fan, you take hand fan or maybe ceiling fan or anything, then you blow. So particle will be heated up, blowing. So hot particle moving up quickly, fresh low temperature particle will come, again it will get heated up, move quickly. So quickly you are removing the hot particle. So cooling rate will be very high. Okay. So H value will be changing, again surface area. So my PhD thesis was on not thesis, actually PhD I have done some work on dimple surface. If fluid is flowing on flat surface, like say when table is there and table is heated up, so cooling rate will be lower. Okay, if cold fluid or air is flowing over it. But if I have roughness on the surface, so cooling rate will be higher. So it is depending on surface also. Okay, like you see this picture I am drawing here, right side. So it is creating loss of turbulence. Okay, when fluid is flowing, turbulence is created. So turbulence will be taking more heat actually. Okay, so your heat transfer rate will be increasing based on your surface area, your fluid medium, or the velocity there. It is natural convection, forced convection, or free convection. Okay, so natural convection, buoyancy, because of buoyancy it will be removing heat slowly. If you are creating forced convection, blowing air, so heat transfer rate will be higher. So H value will be changing actually. Again material, what type of material, wood or metal, surface roughness. So many parameters are there to change your convective heat transfer coefficient. Okay. So QO and QW, water and oil, heat required, Q small, okay, capital Q, required heat. Required heat unit is BTU per hour. Okay, and TM, TM term I have used. TM actually logarithmic mean temperature difference. You may have studied in heat transfer LMTD or logarithmic log mean temperature difference. Okay. So, this Tm, A means surface area of the pipe or tube, whatever you are using. Okay. So, Tm formula I think you should be knowing. Tm degree Fahrenheit, GTD they created short form, GTD minus LTD, LTD divided by log of GTD by LTD. Okay. What is GTD? Greater temperature difference. Greater temperature difference. Okay. Uh, this is GTD and LTD. Uh, LTD is least temperature difference. Okay. So, what is GTD and LTD? Better I will go to next slide. Okay.